Hi, everyone. My name is Gus Diaz, and today I'll be walking you through my analysis of Problem C from our Week 15 spectroscopy assignment. The molecular formula is C6H12O2, and I use IR 13C NMR and 1H NMR to identify the unknown compound. Spoiler alert, we're headed towards a methyl ester with a twist. Let's get started. Our molecular formula is C6H12O2. To calculate the degree of unsaturation, I use the following formula. Degree of unsaturation equals 2 times 6 plus 2 minus 12 over 2 equals 2 over 2 equals 1. That means that this molecule has one ring or one double bond. Since there are two oxygens, I'm thinking this is an ester, probably a carbonyl and an ether-like linkage. We'll confirm that with IR. Looking at the IR spectrum, I noted a strong sharp peak at the 1740 centimeter, which screams CO stretch, which is most likely from an ester. There's also a strong band around 1200 centimeter, which is consistent with a CO single bond stretch. There's no broad OH peak near 3300, so we can rule out alcohols and acids. Together, these signals point directly to an ester functional group, and that matches our hypothesis from the degree of unsaturation calculation. Next up is the 13C NMR spectrum, where we see 5 peaks total, fewer than the 6 carbons in the molecular formula. That tells me that 2 carbons are chemically equivalent, which is a subtle but powerful clue. We have a strong downfield signal at 174 ppm. That's our ester carbonyl. At 51 ppm, we see the classic OCH3 carbon. Other peaks align with CH2 near the carbonyl and branched alkyl chain with 2 methyls in the same environment. This symmetry, along with the ester this symmetry along with the ester evidence suggests a branched chain ester rather than a linear one, such as methyl pentonate. Here's the signal assignment breakdown. 174 ppm, classic ester carbonyl carbon. 51 ppm, a OCH3 methyl group, common in methyl esters. 42 ppm, CH2 next to a carbonyl. 24 ppm, a CH group between 2 methyls. 21 ppm, 2CH3S in an identical environment. These shifts match up with a methyl ester attached to a branched alkyl chain. The chemical equivalency of the 2 methyls suggests a CH between them, a key structural clue. And now the 1H NMR spectrum, this is where everything locks into place. We see 4 signals. A singlet at 3.7 ppm with an integration of 3H, that's our OCH3 methyl group. A triplet at 2.3 ppm, integrating to 2H, a CH2 adjacent to the ester carbonyl. A multiplet around 1.6 ppm, just 1H, likely a CH between the 2 methyls. And finally, a doublet at 0.9 ppm with an integration of 6H. That's 2 equivalent methyl groups. This pattern, especially the 6H doublet and the 1H multiplet, is a textbook signature of a CH-C3-2 group, a branching motif. Here's the proton assignment table. The integration and splitting patterns match perfectly with a methyl ester on one end and a CH-CH3-2 group on the other. That helps us narrow down in on the final structure. The final structure. The structure that fits every piece of data is methyl to methyl butyrate. The carbon count, symmetry, IR, and both NMR spectra confirm it. Each signal matches a specific part of this structure. All the hydrogens match what we'd expect for a methyl to methyl butanate. More specifically, here's how it fits. C6H12O2, so 6 carbons, 12 hydrogens, and 2 oxygens. 1DU explained by the ester carbonyl. IR spectrum confirms the ester group. 13C NMR has 5 peaks with 2 methyls in the same environment. 1H NMR gives us the perfect pattern for a methyl ester with a branch chain. OCH3, CH2, C with a 0, sorry, O, a CH between 2 CH3S and the CH doublet we needed to clinch it. Thank you so much for watching. This was my structural analysis of problem C using IR and NMR to identify the compound as methyl 2-methyl butanate. Good luck with your own spectral sleuthing, and remember, molecules never lie, they just split into multiplets.